Good morning, everyone. This talk is mostly a paper that we presented in the Reconfig conference last year in December in Mexico. It is really an experiment. It's work in progress. It's kind of, what if we could do this with partial reconfiguration? So there's mostly ideas, where we're at, where we would like to be, and some results at the end. So as you may know, we've been working on a message-passing framework that has a core library that provides this message point-to-point protocol processing for message passing. But there are also around it several satellite projects, as I call them. And I'm not going to mention all of them, just going to say that we have co-simulation, profiling, sort of high-level synthesis from MPI to parallel processor engines. There are libraries and applications that other people create on top of Partition-MPI. There is network-on-chip infrastructure, portability, all the plumbing to deliver the messages. And partial reconfiguration is just another of these satellite projects that sort of complement the framework and increase the functionality of the entire library. So the rest of the talk, I'm just going to quickly mention what triggered our interest in partial reconfiguration, and then the rest of the talk is about how do we envision the use of partial reconfiguration within our framework. And then just a quick example of a vector engine that we built to test and make sure that our framework works, and some conclusions. So why partial reconfiguration? Well, as Paul mentioned, Xilinx announced this new flow that's supposed to be easier than the previous one. Apparently, the previous one was not very user-friendly. You have to instantiate macros yourself, very restrictive. And then, so they announced, well, let's see what we can do with it in our flow, the current PR flow, and how that integrates with ours. But also, then Xilinx announced the largest Vertex 7 FPGA, and then I was actually surprised how big this device was. It has 1.2 million lots, 2.4 million flip-flops, over 1,000 VRAMs, and the bitstream size is 54 megabytes. I mean, you compare this bitstream size with the bitstream sizes that you work currently. So, and this is using this technology, which is also quite interesting. It's silicon stack interconnect technology where you can put several FPGA dies per device. So that allows them, and they have a silicon interposer where they interconnect these devices. So this allows them to create these really massive FPGAs. I mean, and I guess this goes into the trend that FPGA devices device sizes increases. And FCCM conference this year, I believe they have this special, it was encouraging the submission of papers about what would you do with a 1 million lot FPGA. So that was what triggered our interest. So maybe it's easier to deal with small portions of the FPGA rather than the whole thing, because this could be clearly challenges for CAD tools. So now let me move really high up in the scale of abstraction from low-level hardware design to high-level parallel programming, because our message passing framework is based or inspired by MPI. So MPI stands for Message Passing Interface. It is basically a parallel programming model where you have a set of MPI processes that communicate via messages, and then written in C, C++, Fortran, you compile it, you run it in a cluster or a supercomputer. Now, when we mix FPGAs, we come up with Arches MPI, which also takes MPI processes, parallel description of an application, and maps this into a heterogeneous set of computing elements, high-end processors, embedded processors, or hardware accelerators. And they can exchange messages in point-to-point fashion, following the same model. So this is what we had. And now, with partial reconfiguration, what we have achieved is some sort of hardware reuse. That was our first step in using partial reconfiguration. So what we can do now is at runtime, without disrupting the rest of the FPGA, we can change or replace one hardware accelerator by another, reusing the same hardware resources in the FPGA. And we can do this back and forth as necessary. So in this case of an application, in a case of an application needs a different kind of accelerator, you can partially reconfigure it. So that was the first step. We achieved this, we did this. But this is not the only thing we can do with partial reconfiguration. This is just the first step towards something else. And this is one of the things we would like to have working as well. Easy parallel application launch. This is not yet implemented. But this is, for example, how in MPI you would actually start an application, a parallel application. You would say MPI exec, and you say the number of processes 2 of this foo.l file, and 3 of this bar.l file. And then you have 5 processes, and they communicate each other. Parallel application completes, and that's it. That's very easy to launch the application and perform scalability analysis, for example. How well your application behaves with 5, 6, 7, 8 processors. So something like that we would like to have with Arch MPI. So in this case, we would like to implement our MPI exec with, say, 2 foo.l files and 3 bar.bit files. Here the analogy is that elf and bit files, this is a partial bit stream, so they are both binary executable files. The L file is loaded by the operating system and executed by the processor. The partial bitstream file is loaded by the Arch MPI library and executed by the FPGA fabric. But the idea is that with this, we can say how well your application performs with 3 engines, 4 engines, n engines. So that would make very easy to launch applications. So, and another thing we would like to do is sort of an extension of the previous one, is dynamic process creation. MPI, in the MPI 2 standard, they introduced dynamic process creation with this function. The idea of this function is that if there is a sudden increase in the workload, you can just spawn software processes and deal with this increase in the workload. So in Arch MPI, what we would like to do is, if we have a system like this running with 2 hardware engines, 1 microblade, and 2 processors, and if we have a sudden increase, for example, that requires the automatic creation or spawning of hardware accelerators, we can do this at runtime. And when the workload decreases, we can just terminate the processes. And we can do this back and forth again as necessary. Another use for this, imagine a video pipeline where you have 2 filters, for example. And then if you want to increase, add another filter, you can do it also in the pipeline, right? Without disrupting the current flow of the video. So now you have more filters to go through. So these are the kind of things that we thought could be nice to work with partial reconfiguration. But how do we do all this? So we came up with this template-based bitstreams, which is a collection of pre-built, pre-routed, pre-designed collection of built FPGA bitstreams, where we have a static region and dynamic region. Dynamic regions are those that we can partially reconfigure. And you can think of them as empty slots that we can just fill in the blanks with a user application. So we can have different configuration, 1 for many of those dynamic regions. And one of these dynamic regions we're going to be filling with a reconfigurable module, which is an implementation of one of these MPI processes. So we can reuse one of these template bitstreams for different applications, because the idea is that they are generic. So we can download one of these bitstreams to one FPGA and reuse it for so many different applications. So is this possible or not with the size of an FPGA like the ones that I showed at the beginning? So then we grab these bitstreams and put them in a system with that they can connect with FSB or PCIe or QPI later on, and then they share memory with the processors. And the idea is then we map this file application into this architecture, this hybrid architecture. And executable files are mapped into CPUs, and partial bitstream files are mapped into dynamic regions. These are examples. I don't know if you can turn off the lights maybe. Yeah, much better. So yeah, these are examples of actual plan ahead snapshots, which is very easy just to draw the region that you want to. These are the dynamic regions. You just draw them, and you assign an NGC, a netlist, into those regions, and that's it. You have a partial bitstream. And it is 1, 4, 8 dynamic regions. The rest is the static logic. To give you an idea of the size or the dimension, this is the largest, this is the Virtex 7, largest Virtex 7 FPGA. And this here is a dynamic region with the resources equivalent to the smallest Virtex 5 LX30. So this is, it just gives you an idea of the scale of how big this can be. Or you can have larger regions, of course. But here you can, I draw these to match the lots, roughly the flip-flops, because the fabric of the Virtex 7 has twice as flip-flops as the Virtex 5, the same number of VRAMs and twice the number of DSPs. But then you can have this. You have 7 vertically and 5 horizontally that give you 35 dynamic regions, each with the equivalent size or resources of the smallest Virtex 5. So you can play around with different layouts and generate bit streams. So what goes into the static and what goes into the dynamic region? This shows sort of like the basic infrastructure to get the message passing model working on an FPGA. What would go into the dynamic region would be the hardware accelerators and perhaps embedded processors. We haven't done this. It would be nice to try and experiment and see if we can partially reconfigure an entire embedded processor in one of these dynamic regions. But this is the only thing that goes into the dynamic. The rest goes into the static region. We have the routers, the NOC routers, the actual FIFOs that connect the routers, off-chip communication controllers, off-chip memory controllers, clock generations, etc. All the infrastructure around it that sometimes might be very tricky to get, for example, the FSB, PCIe, or the LVDS, the multi-gigabit transceivers, all the constraints, the timing, the placement. So that can be very tricky for non-experts in hardware. Even for hardware people that can work on hardware accelerators, they might not be familiar with how to constrain these kind of interfaces. They are very optimized sometimes. So we can put all this in the static region, and let the user only worry about the dynamic or the user logic. Now, if we zoom into the hardware accelerator, there is an MPE, which is the message passing engine. And basically, an MPE, a message passing engine that provides the MPI functionality to a hardware engine. And together, the MPE and the hardware engine make up one of these nodes in the MPI programming model. And basically, you have a control state machine that issues commands to the MPE, like send, receive commands, and the data goes through these 5 flows directly into the main computational pipeline. And there are control signals like reset, VC, done, enable. This is the typical use. Now, this is important because based on how much logic of the engine we put into the dynamic region or into the static region, we can have generic or specific templates. So in this case, the entire dynamic region, the entire logic of the engine is dynamic. So we can create generic templates because all the logic of all the engines can be replaced. There is nothing application specific outside the dynamic region. Now this has some challenges. For example, it is recommended that a reset is asserted after you partially reconfigure a region. But we cannot use the global reset because the rest of the FPGA is still working. So we cannot reset the rest. So we have to generate local resets. And a nice trick to generate these local resets is using a shift register, initialized all to the reset value. So say if the reset value is active high, then the shift register will be initialized all with ones, and then it gets connected at the input of the shift register to the global reset. If the FPGA is running, the global reset should be 0, the asserted. And then after n number of cycles, then the logic will be automatically come out of reset. So this is a nice trick to generate the local reset and to generate bitstreams. But we don't have to put all the logic of the engine into the dynamic region. We can have some of the logic in the static region and only partially reconfigure the main computational pipeline. So for example, in a video filter, you know the video filters are very similar. And the only you have to change sometimes is just coefficients or the actual pipeline. But the communication pattern, the other logic might be common to all of them. So that way, some of the logic of the application goes into the static region. And then that makes the whole template application specific. But then which one to use, it's up to the user what he wants to create. You want to have a generic template bitstream so you can reuse it with different applications, or you can have a template bitstream that is application specific. The important thing is just to provide that option. Another feature, or another nice thing we can have by virtue of having a message passing infrastructure is that we can perform synchronization, data storage, and restore. In this case, for example, we have an x86 and 2 reconfigurable modules. So in this case, the x86 processor sends a message to the reconfigurable module A. And then the reconfigurable module says, okay, let me see if my pipeline has been flushed or if I'm not still computing. Because you can perform partial reconfiguration, and if the engine is still busy, you're going to lose data. So there has to be some sort of synchronization. And then, so the engine sends another message saying, back to the processor saying, okay, now it's safe to do partial reconfiguration. And along with this message, the engine can also send the value of registers, of memory, of VRAMs, for example, that the engine would like to keep for a later time when the engine comes back into the running state. So at that point, the processor then performs partial reconfiguration, and then it sends a message to the newly reconfigured module. Reconfigured module A no longer exists. Now reconfigured module B is now in place, and the configuration of the message can be used to restore the data that reconfigured module B might have stored before. Now, in this case, the configuration is initiated by the processor, because the processor knows when partial reconfiguration needs to take place. Now, by having, again, a message passing, a point-to-point message passing, where anyone in the message passing could be a master or a slave, then the engines can also trigger partial reconfiguration. So in this case, you have a reconfigurable module A, which can send a message to the processor saying, hey, I need to be reconfigured. This is a request to be reconfigured. And this message can be used also to store the data that later could be used. Then the processor performs the partial reconfiguration process, and it sends a message back to the reconfigurable module B. Again, with the data to be restored. An example, which one to use, again, it depends on the application. The reconfigurable module initiated approach could be, I don't know, it might not make sense what I'm going to say, but imagine a bit packet inspection engine, that an XML parser, and you receive XML packets, and that's fine. And then suddenly it starts receiving video packets. And the engine might not know what to do with video packets. Then it can request probably a partial reconfiguration for another engine to kick in and say, the video processing engine. So I don't know if that makes sense, but the idea is just to show that the engines can also trigger based on a condition or a threshold or something. They can know when partial reconfiguration needs to take place. That can be very easy as just sending a simple message. That is a command to the MPE. So send the request for configuration message, and then the processor will just react to that. One of the things is that we wanted to really make it really portable. We have suffered the problems or the issues of having to port our applications from one platform to another, from one PCI platform to an FSB platform to et cetera, over 3 or 4 platforms. I think we have already migrated a certain application, and it's very difficult. So we wanted to provide a way to do partial reconfiguration in a portable way. So the user application just have to call one function and pass in the partial bitstream file, which can be downloaded from the internet, from the network file system, from wherever, because it's an x86 processor, and then provide the board ID and the FPGA ID. Remember that we're thinking high performance computing, so we can have multiple boards, and each board may have multiple FPGAs. So, but that's all you need from the user perspective. That's everything that needs to happen. Plus, obviously, the synchronizations by sending explicit messages, if needed. And then we have the software middleware layer and the hardware engine on the FPGA that they synchronize and they exchange information. So the bitstream is DMA'd in from this engine, and it's sent to the ICAP interface if the reconfigurable region is in the same FPGA, or it is sent to the select map interface if the dynamic region is in another FPGA. But this is all transparent for the user. The user doesn't really have to care about whether you're using PCIe or FSB, or if one engine is in this FPGA or the other. The vector engine, this is a very simple engine that we used just to make sure that everything was correct, that we send the bitstream file and all that. It's an example of the application-specific case where part of the logic is in the wrapper, is in the static region, and only the pipelines of the engine are the dynamic region. It has 4 pipelines so that we can perform 4 floating point operations per cycle. And each pipeline has a reconfigurable module. So we have 12 partial bitstreams in this case. And we would just partially reconfigure the pipelines with the addition reconfigurable module, then replace it with the subtraction, and then replace it with the multiplication, and see that all the results are correct. And then, so that's very simple, and let's see how it goes. This table is very simple. It basically shows that the more you perform partial reconfiguration, the more overhead you're going to have in your application. With FSB, you have less overhead than with PCIe, obviously because of the higher bandwidth. That means you can perform partial reconfiguration faster with one and not the other. In this case, we perform 100 load, operate, store. So that means load, accumulate, then store back the results, or load, subtract, store back, or load, multiply, report back of the operations. Each vector was 4,000 floating point numbers. The bitstream size of each of the pipelines is this. So we have to send 4 times these bitstreams. So yeah, but this is not really important for people. It's more important for us as a benchmark, so that when we improve the framework, we'll know if how much we improved or how much we made it worse. More interesting is and disappointing at some certainly was the place and route time, for example. I don't know if you can see this, but the first configuration is, the first place and route time is for the whole template bitstream, which is took 3.5 hours to do place and route. And I said, okay, it's the template bitstream, the whole thing, that's fine. But surely the dynamic region, being that small, it's going to take way less time. And it took 1.5 hours. It had to generate 4 partial bitstreams, so each bitstream took around 25 minutes to generate. But the problem is that if you generate the whole vector accumulator system without partial reconfiguration at all, it takes only half an hour. So, yeah, the tools are not perfect for sure, but we were assured that these times we will decrease drastically from future releases. So that was in the 12.1 version of the tools. Now it's 13.1, and so I'm really anxious to go and see how long it takes now. So,
how big is the system in lookup tables or some?
which system? The
entire system. The whole system. How big is it?
This system?
Yes.
I don't remember from the top of my head the actual resource utilization of the whole thing.
Yeah.
But we were told that the system was accounting the whole system, the whole net list. It was processing the whole net list, even though it was just generating one partial bitstream. But yeah, I don't know.
Sure.
I'm
just curious. It gives good context for output versus outcome.
This is really tiny, really. It's not that big. It's not that big. Yeah, so that was the problem. And in conclusions, we developed a working framework for people to use PR. And this can be said very easily, but a lot of PR research is on theoretical studies or simulators. But really getting PR to work has a lot of details. The framework has portability, because it doesn't matter if it is PCIe or FSB. It's very simple. For us, it's going to be now transparent which platform we're going to use. We can just say, reconfigure this engine, and that's it. There are two ways to perform partial reconfiguration: processor initiated or initiated by the hardware. Which one to use depends on the application. Important thing is that it's ported, we can do it. Messages can be used to store and restore data. You can think of push and pop data out of the stack before a context switch. So this could be very useful for virtualization of the FPGAs later on. The same generic template bitstreams can be used for different applications. I really wanted to have 4 different applications I was working on. I trusted high-level synthesis tools. I was working with ImpulsC to get the applications really quick. It failed a little bit, so I didn't finish the application sometime. But I wanted to show different kind of applications. I was working on an edge detection, the trapezoidal method to compute the area, approximate the area, Jacobi iterations. So I wanted to have different applications that would run on the same template bitstream, just to prove the point that it can be done. Template bitstream may reduce the development time. Focus only on the application engine. Forget about the system level integration, how you're going to transfer data from one point to another. Just focus on the application engine. That would certainly reduce the development time. And I think if we just bring high level abstractions into the FPGA domain, we'll just make them easier to use, like the MPI-exec, so we can launch applications in FPGAs like really easy. That will make FPGAs way easier. So yeah, thank you. If you have any questions. Yeah, Professor.
Oh, okay, so can you elaborate a little bit more on the template bitstream that you have and how easy it is to generate and replicate? I assume in the ideal case, because you're doing an NOC and each of the configurable region is actually doing the same function, right? So you could ideally replicate a bitstream. I know it's not that easy at all, so I'm just wondering if, in practice, how actually you did it.
Well, to generate a template bitstream, it's really easy. You can just draw the regions, and then outside the region, it's the MPE. And outside the so you just in the plan ahead, you just draw that,
yeah,
and that's it. All you have to do in plan ahead now is just assign what netlist goes into what region.
So what if I have a netlist that can replicate it everywhere?
Yeah, so you have a netlist. The same netlist can be assigned to 4 regions, for example.
But I only have to do place and route once. Or
no, that's a problem. You have to run place and route for each one of this. That's why it took so long. Because for 4 dynamic regions, it was running 4 times place and route. The tools were not clever enough to say, okay, it's the same netlist. Why don't you just run place and route once and just replace the XY location in the bitstream for each one of the regions? So it doesn't seem they do that because it takes a really long time. But definitely it would be one way to speed this up. You have same netlist, replicate it in something like this. I don't want to see how long it will take to place and route that many regions. So
the thing is that it seems that it's impossible for the user to do something about it.
Well, at this point, yeah. But I think this is just there is research that people can. I don't know how they did this because obviously I think the bitstream information is not disclosed. But they have filters that, as the bitstream goes through the filter, they can replace the XY location so that they can put the netlist in different places, sort of like a relocatable executor.
So the architecture actually supports that you can relocate?
You can, if you knew which parts of the bitstream to toggle, you could probably do that, right? You just grab the same template, as long as it is the same, you use the same resources. And you use only flip-flops, for example. If it is the same flip-flops, it's like an RPM, like a relative placement macro. You just change the actual location.
Well, that's what I was asking, is does the underlying fabric support that? It is identical,
If you use,
except that it's a different location.
If you draw the rectangles correctly.
yes, I guess, yeah, if you drew the rectangle correctly. Yeah, do you have another question?
Yeah, I did. It's a little bit related, which is your notion in those little squares is that you can drop in different engines, but the interface of those engines, the placement and the routing, external to that is fixed, right?
Yes.
And so, can you talk? Do you know anything about how hard the router has to work to make that to route to make that interface work? Is it done? Well, I guess the question is it done with actual wires, or is it done by flowing through logic? Do you know how that interface is enforced?
See, for example, in this case, this would be dynamic.
No. So the question is a low-level question about the wires.
Yeah.
The connectivity of
Yeah.
the wires.
So this is dynamic, this is in static, and the interface in between them, there's a lot macro. It's a lot. There's one lot that is instantiated by the tool. And so all the signals that cross the boundary between static and dynamic are inserted automatically by the tool. That was the difference before against the previous flow. In the previous flow, you have to instantiate the macros yourself. In this case, you just say, here's my NGC of this netlist.
Okay, so the answer to my question is, logic is at the boundary.
Yeah,
So
there's a lot.
Yeah,
There's
it's
one lot
not, it's
that
not a
goes.
wire, for example.
It's not a wire, it's a lot. And then it's advised that you sort of register before and after the lot for timing purposes, if you like. But that's an option. Yeah.
So going back to that relocation of bitstreams, right?
Yeah.
We had a talk
Yeah.
at the guy from
The guy from Xilinx who was
he
presenting
said
that.
there's a fabric and limitation, like in terms of timing. The timing will not hold.
No, that was Arun's question. Arun was saying
Right.
if you relocate one NGC from one region to another, there might be timing variations
Yeah.
based on how far you are from the clock tree and things like that. If you're really high speed, for example, right? But within a certain, I guess, range.
So there has
I
a
mean,
tolerance. You would have to
Yeah, I think
say
you
you
have
would
just-
have to back off from the max Fmax and
I think
say
so. Yeah.
I'll go 180 and then maybe I can go everywhere, right?
Yeah. I know that I've read some papers that have done that in Vitec Supro. I think that's when the first time the partial configuration started in.
But then the
But-
tool has to really help you with that, right? You can't just like then change the X and Y. The tool
Yeah.
has to really help you and tell you like there are limitations.
Yeah, there might be timing violations for sure that you don't know, right? But
So if timing violations can happen, then you have to look at some place in route time. Then you have to look at each dynamic region and see, like, or you can ahead of time just know that it's 50, like you have to like go 30 megahertz lower, and then you don't have to actually do.
yeah, exactly. Yeah, no, I mean, I'm not saying you can run timing analyzing now, post place and route after this. I don't know how this is gonna be solved, but sure. I mean, if this is really an issue, we've asked this question to Xilinx themselves. So, but you cannot really do that because of the clock thing. And they said, no, sure. I mean, you just have to run really high speed in order to get into trouble, right? If you run like 133 megahertz, 150 megahertz.
But you need still some guarantee if you want to deploy
Yeah,
this.
of course. Yeah, yeah.
Hope that it.
Oh yeah, for sure. Yeah, I don't argue that.
So I have a couple low-level questions as
Yeah.
well. So on both the output side and the input side, is there an LCL, like a LUT that's
Yeah.
inserted?
Yeah.
So both ways?
Yeah.
And another question is clocking. Can you change the clocking in a region? That's a tricky thing with partial reconfig.
Yeah. Like
So-
one clock for the dynamic, one clock for the static, you mean?
I have two different dynamic regions that are going to go in the same, we call them partial reconfig instances. Okay,
Right.
so they go in the same region and time, I'm going to swap them one over top of the other. And probably not in this application, but in many applications, it's desirable to be able to change the clocks when you do that,
Right.
especially if you're talking to I/O. So I don't know if you're familiar at all. Is there any provision for changing the clocks within the region?
I really haven't thought about changing the clocks. All I can do, I guess, is just if you have asynchronous FIFOs in here.
I guess this is a different one. But in your application, I don't think you need to do it, right? But in many applications, some of the most compelling ones for partial reconfig, you're talking to, say, high-speed transceivers, and you're changing your communication protocols, and it is fairly fundamental that your clocking is actually changing as
Right.
you do that. So I'm curious, because we're facing this we're working on this right now, so I'm
Yeah.
curious whether or not, like, the Xilinx flow supports
Well,
it. So,
yeah.
Actually, so the way the Vertex 5 clock tree works is that with every cell, you can access up to 10 clocks, for
Yeah.
instance. And so what you would have to do is in your template bitstream, you would have to have provisions to have all variations of the clocks that you want. Maybe have one global clock, and then on one of the secondary clock nets have a switchable PLO or something like that. And then your partial config logic would have to select which of the clocks it wants to use. You don't always have to use which of the 10 clocks that you want to use. Because in every, not even reconfigurable region, but in every clock region, you have access to 10 clock nets. So through that, you could select which clock you want to use, but it would have to be supported in the framework bitstream.
Okay, thanks.
More questions?
Okay, so thank you, speaker. So this month's pizza is sponsored by Professor Zhu. So thank you, Professor Zhu.